Hello friends, in this video let us discuss about the equivalent circuit of your single phase induction motor. So the equivalent circuit for your single phase induction motor can be obtained from two methods, because we know in a single phase induction motor there are two theories, namely one is double revolving field theory and another one is cross field theory. So firstly we shall develop the equivalent circuit on the basis of double revolving field theory. So when only the main winding is excited. So now consider the case when the rotor is stationary and only the main winding is excited, the single phase induction motor behaves as a single phase transformer. Once again I am repeating, consider the case the rotor is stationary and the rotor windings are short circuited and only when the main winding is excited. So similarly in the transformer, the primary is excited and the secondary is not given any supply, it is stationary. So on the principle of electromagnetic induction it works. So like this, similarly here the main winding is excited and the rotor is kept stationary, then the single phase induction motor behaves as a single phase transformer. So if you look the equivalent circuit for your single phase transformer, here V1 is a supply being provided and I1 is a current flowing, and this is stator, that is the main winding resistance, this is the main winding leakage reactance, this is the magnetizing reactance, and this is the rotor resistance referred to the main stator winding, and this is leakage, that is rotor leakage reactance referred to the main stator winding. So here the core loss is assumed to be lumped with the mechanical and stray losses as a part of rotational losses. Now according to double revolving field theory, a stationary pulsating magnetic flux can be resolved into two fluxes of equal magnitude but in opposite direction. So the air gap portion in your single phase induction motor can be split into a forward rotating flux and a backward rotating flux. So the standstill, at standstill, if you know the slip is equal to, I know the slip is the ratio of difference of synchronous speed and actual rotor speed upon synchronous speed. So at standstill I know my NR is equal to 0, therefore I am having my slip is equal to 1 at standstill. So at standstill you do not have the effect of slip into your equivalent circuit diagram. Now when the air gap portion is split into two parts, or the rotor of your single phase induction motor can be assumed as two imaginary rotors. So one is a forward rotor and the other one is a backward rotor. So the impedance seen by the rotor at standstill condition will be given by R2 prime plus jx2 prime, R2 dash by jx2 dash, because this is due to the forward field flux, and similarly for backward field flux also it will be by 2 and by 2. Now if you consider this is your, that is R2 prime by 2, that is the rotor resistance referred to the main stator winding, and this is rotor leakage resistance referred to the main stator winding, and here this is your core loss component and this is the reactance magnetic reactance. Similarly here for the backward field flux R0 by 2, and for here Xm by 2, this will be R2 prime by 2, that is the rotor resistance referred to the main stator winding, X2 dash by 2. So here this is the main stator resistance and leakage reactance. Here the supply is V1 being provided and the current I1 is flowing here. So this current will be I forward, IF, and this current will be I backward, IB. So according to double revolving field theory, we have split our air gap portion, or the we have split a pulsating stationary magnetic field into two fluxes. So this part shows the effect of forward field flux and this shows the effect of backward field flux. Now the forward field flux induces a voltage EMF and a backward field flux induces a voltage EMB in your main stator winding, and if I say the resultant voltage is indicated by EM, then the resultant voltage in the main stator winding is a summation of the two fluxes. So this flux induces a voltage EMF and this induces a voltage EMB. So at standstill condition both are equal. That means you are having EMF is equal to EMB and EM will be twice of EMF or EMB. Now I know that my single phase induction motor is not self-starting, because if you go to the torque slip characteristics, then you know that the forward field torque is like this. Here you are having slip S is equal to 1 and the backward field torque will be like this. So this is the forward field torque and this is your backward field torque. So the resultant torque will be like this, and at standstill condition where slip is equal to 1, the resultant torque will be 0, and hence the single phase induction motor is said to be not self-starting compared to a three-phase induction motor for this reason. So to start the induction motor, what we are doing is we are providing a auxiliary winding. So the two windings are present now in the single phase induction motor, and as the two windings are displaced by 90 degrees in space, and also the supply being provided, the supply current is also displaced by 90 degrees in displaced apart equally in time domain, and this is the windings are distributed equally in space domain. So a rotating magnetic field is produced and the motor starts rotating. If your forward field torque is greater than backward field torque, then the direction of rotation of the shaft will be in anti-clockwise, and similarly if the backward field torque is greater than forward field torque, then you are having clockwise direction of rotation of the shaft. Now if I do not involve or if I do not employ auxiliary winding, I would like to start the motor, then I have to spin the motor in the direction I require to start the motor. So you have to give mechanical spin to the rotor if you are not employing a auxiliary winding. So as the voltage picks up, the motor gathers the torque and the motor starts rotating. So this is due to the forward field flux and this part is due to the backward field flux. But here the core loss component has a very high value, that is this value has a very high value. So the current, as we know, the current prefers to flow through the low impedance path. So this will be assumed as an open circuit here, and the current starts to flow through the magnetizing reactance of the both forward field flux and the backward field flux, as it doesn't affect much in our calculations this core loss component. So if I consider the slip for the forward field flux, my slip will be equal to Ns minus Nr upon Ns. This is SF. Now similarly, if I go for the backward field flux, then it will be S backward is equal to Ns minus, and the direction of the rotor is opposite to the rotating magnetic field, so I am writing negative Nr upon Ns. Now from here SF I can write is equal to 1 minus Nr upon Ns. So if I write similarly here 1 plus Nr upon Ns, so from here Nr upon Ns will be given by 1 plus 1 minus S, that is equal to 2 minus S. So 2 minus SF. So this is your backward field flux and this is your forward field flux. Now if I consider my slip after starting the motor, then I can have here R2 dash by 2s, here R2 dash by 2 into 2 minus s. So after considering slip, you are having the slip as 2 minus s for the backward field flux, and as a slip s is equal to your forward field flux. So this is the double revolving field theory equivalent circuit for your single phase induction motor. And now if you want to calculate the calculations based on this equivalent circuit, if I say this is my forward field impedance and this is my backward field impedance, then to calculate the stator current, that is I1, I know the stator current can be given by the voltage applied at the stator terminals upon the total impedance of this equivalent circuit. So if I consider the impedance as this as Z1 and this will be ZF plus ZB. Here these two are in series and these two series and they are parallel with your magnetic that is magnetizing reactance, and here these two are in series and they are parallel with your magnetizing reactance. So applying series parallel combination, you can calculate the equivalent resistance, that is ZF here and ZB, and if you write here V upon Z1 plus ZF plus ZB, you can get the stator current. Now I got the stator current. Now to calculate this input current, that is the input current given here, P is equal to stator voltage V into stator current into cos theta, where theta is the angle between stator voltage and stator current. Now the power generated or the power developed will be given by the difference of, if I say the power dissipated into this resistor is P of, that is the equivalent or the effective rotor resistance referred to the main stator winding is R2 dash by 2s, and here the effective rotor resistance referred to the main stator winding is R2 dash upon 2 into 2s. So the power dissipated in this resistance is P of, and here it is PB. So my P generated or P developed can be given by the difference of these two powers dissipated in the respective resistors. So this is my P generated. Now the copper loss, P copper loss can be given by slip S into PG. So this is your copper losses incurred in the stator winding and the rotor winding. Now if you want to calculate the output shaft power, then the output power is given by the P input to the rotor minus S into your PG minus the rotational losses incurred in the rotor part. So this is your output shaft power. Now if I want to calculate the efficiency, my neta will be given by the shaft output power to the input power applied. So this gives your efficiency. So this is all about your equivalent circuit for your single phase induction motor. So I hope you understood well. Please subscribe to the channel. Thank you.